Periodic relationships among the elements. So the periodic table summarizes much of what we know about the elements. When the elements are arranged according to increasing atomic number, periodic patterns of properties become evident. The table's iconic arrangement permits an easy prediction of elemental properties then. There's a relationship between the periodic table and the quantum theory of an atom. The periodic table in the picture here is shown using energy levels. So hydrogen and helium, whose valence electrons are in the first energy level, are closest to the nucleus. And then you have your second energy level, and your third in yellow, and your fourth in green. Then it tends to get more complicated as you get into the transition metals. But that's just one interesting way of organizing the elements. So elements with similar electron configurations behave similarly in the respects, and in general the properties of the elements exhibit observable trends. So in the 19th century, chemists only knew about the masses of the elements, not atomic numbers. So it makes sense that they arranged the elements by the known mass. John Newlands was an English chemist, and he found that when arranged by mass, every eighth element had similar properties, called the law of octaves, oct meaning 8. However, his ideas of the every eighth element fell apart when you got past calcium. So this law of octaves wasn't really accepted. Dmitri Mendeleev and Lothar Meyer both worked on a periodic table, Mendeleev being Russian, Meyer being a German chemist. They both worked on it at the same time, but separately. And they grouped the elements more accurately according to the properties. So not only did they line them up, but they also grouped them in columns. And Mendeleev is given more credit than Meyer because he also predicted the properties of some of the undiscovered elements. And he was pretty accurate with his descriptions. There's one story where he predicted the properties of element 31, which is the one underneath aluminum, and he wanted to call it, oh no, I don't remember the name he wanted to call it, like pseudo-aluminum, or there it is, Eka aluminum, EKA aluminum, to mean that it came right underneath aluminum and it shared properties. But the person who actually discovered element 31 ended up calling it gallium, and Mendeleev was very upset by this. So there were some issues with Mendeleev's periodic table, and that's because he arranged them by atomic mass, and those weren't always accurate. And ordering just by atomic mass put some elements in families they don't belong to. For example, argon and potassium would have been switched, but that doesn't make any sense because argon is a noble gas and has properties of noble gases, where potassium is very reactive. So Henry Moseley, another English chemist, discovered a correlation between the atomic number and the frequency of X-rays generated when you bombard your atoms with high-energy electrons. In other words, he determined the atomic number for the elements that we didn't know about. The modern periodic table then is arranged by atomic number and fixes the discrepancies that we had with Mendeleev's. Electron configurations also help to explain the reoccurrence of properties. So that's really where we're going to start heading, is looking at our periodic table and looking at the properties. Now this periodic table here is color-coded based on when the elements were discovered, and I just think that it's interesting that some of our elements really weren't discovered until much later. For example, number 43, that was a golden child or golden element. Everybody wanted to figure out what 43 was because we knew about all the elements around 43 for such a long time. And there was quite an argument when it actually was discovered. Also, another interesting element is seaborgium, which is number 106. Seaborgium is the only element that was named after a living scientist at that time. So Seaborg is a chemist, and he was actually honored by having an element named after him. There are other elements that are named after scientists, but they had already passed when they were honored with that. So periodic classifications of the elements. Elements are categorized in some big chunks: representative elements, noble gases, transition metals, lanthanides, and actinides. Representative elements can also be referred to as main group elements. These are elements in groups 1A through 7A, or the ones that have incompletely filled S or P sublevels of the highest principal quantum number, N. Noble gases are group 18 or 8A. Transition metals are groups 1B and 3B through 8B. They have incompletely filled D sublevels. Group 2B, which is our zinc group, so group 12, is actually not truly transition metals or representative elements. It doesn't really have a family name, it's just kind of sitting there. Lanthanides and actinides are what we refer to as the F block transition elements, also called the inner transition elements, because they would go back into the transition metals if we were to place them back into the periodic table. And they have incomplete F sublevels. So here is a periodic table color-coded with those main groups. Again, notice that group 12, which is our zinc, cadmium, and mercury, aren't really belonging to any of the other groups. Valence electrons are the outermost electrons, and people in the same group or family have the same number of valence electrons. So group 1 has 1 valence electron, group 2 has 2 valence electrons, because we would form 1s and then 2s. Group 13 would have 2s and p1, so it has 3. 2s and p2, so group 14 has 4. 2s and p3, so 15 has 5. 16 would be 6, 17 7, and 18 8. There's 2 exceptions to that though, and that would be helium only has 2 electrons. So even though it's in group 18 because it's a noble gas, it has a full S sublevel, which is why it's a noble gas. So it's only has 2 valence electrons. And then everybody in the D block, or 3 through 12, has a full S orbital coming before it. So 4s2, and then you get into the 3d. Well, 3d would be one less energy level. So everybody in the D block actually has 2 valence electrons because of the S orbital that is filled prior to it. So we have valence electrons, which we refer to as the outermost. The core electrons are all of the other electrons that are not in the outermost. So not all elements in a family actually will have the same chemical properties. Group 14 is a classic example. So you kind of do need to look at what type of elements are in that group before you make your decision. Carbon is a nonmetal, then we have some metalloids, and then we have some metals. So they really don't share a lot of common properties because there are actually different types of elements in there: nonmetals, metalloids, and metals. Noble gases behave very similarly. They all have full outer shells. Helium has a full 1s, the rest have full p's. Helium and neon are chemically inert, but the others can actually form compounds. The other noble gases, not helium and neon, have access to our d orbitals, which gives them the option to form compounds, which helium and neon do not. We'll talk about more in our next unit. So the transition metals have no regular pattern in the families. All of the transition metals, instead of just looking at the families, all of that area share many characteristics that sets them apart from other elements because they have unfilled D sublevel. And again, that's why we don't include the zinc family, because they have that full D sublevel. So they're a little bit different from the rest of them. Lanthanides and actinides, again, not looking at the family, but looking at that whole area, both of those 2 rows share characteristics because they have unfilled F sublevels. So an atom with a certain element has 20 electrons. So without looking at the periodic table, let's write the ground state electron configuration. 1s2, 2s2, 2p6, that's 10 electrons. 3s2, 3p6, that's 18. So 4s2 would be the ground state electron configuration. So classify the element. Well, because it's 4s2, I know that it's going to be a metal. I also know that it's going to be an alkaline earth metal. So determine if the element is diamagnetic or paramagnetic. So you have to remember, paramagnetic, you have a lone electron. Diamagnetic, they're all paired. So because we end in 4s2, it's going to be diamagnetic because all of the electrons are going to be paired. Alright, representing free elements in the chemical equations. So when we write our reactions, how do we know what symbol to use if we're just referring to the element by itself, not in a compound? Well, metals actually exist as very complex 3D networks, and we use their empirical formulas. In other words, elements, we just use a symbol from the periodic table. So if we're talking about iron, we're just going to write Fe. We don't put charges there, we don't put anything else with the symbol. If we're just talking about the elemental metal, we just use the symbol. Now if we're talking about non-metals by themselves, there's no single rule for this, so it gets kind of complicated. Carbon actually also exists as a 3D network, and depending on the structure of that network, we get our different forms of carbon, graphite and diamond. However, we still just use the symbol C for carbon. And you've seen in the formula, in the reactions, sometimes they actually write out the word graphite or diamond to tell you which type of arrangement we're looking at. All of our halogens, hydrogen, nitrogen, and oxygen, exist as your diatomic. So in Chem 1 we teach you Hofbrinkel, or if you look at element 1, that's hydrogen. If you go to element 7, that's neon, and then if you draw 7, oxygen, fluorine, and then go down, chlorine, bromine, iodine, there's all of your 7 diatomics. Now, element 85 is in the group 17 are halogens, but it's not a halogen, so it's not included there. Phosphorus actually exists as P4 because that's the most stable state, so it's a molecular type of atom. So when we write our reactions, really when we refer to phosphorus, we should be writing P4. That's something new from Chem 1. Sulfur uses the empirical symbol S. However, sulfur actually exists in the stable form of S8. So sometimes you might run across reactions where we show the stable form of sulfur instead of the empirical formula or just the symbol. All noble gases are monatomic species, so all noble gases just use the symbols. Metalloids, like metals, have very complex 3D networks, so we use the symbols to represent them. Alright, so electron configurations of cations and anions. Ionic compounds are made up of cations and anions, so it's helpful if we know how to write the electron configurations for them. We're still using the same rules as for neutral atoms like we did in our previous unit. Ions derived from representative elements. That would be, remember, groups 1, 2, and then the 13 through 17. Most have noble gas outer electron configurations. So you have your energy level S2, your energy level P6. So that would be our noble gas. Cations have one or more electrons removed from the highest occupied sublevel, or energy level, So if we look at sodium, sodium's electron configuration would be neon 3s1. So to be like a noble gas, it's going to lose its one valence electron, and so we would write Na plus is simply neon. Anions have one or more electrons added to the highest occupied energy level so that it turns into a noble gas. So fluorine is 1s2, 2s2, 2p5. So it's one away from being a noble gas, having the P6. So it's going to gain one electron. So F minus is 1s2, 2s2, 2p6. In other words, it's neon. So sodium plus, fluorine minus, and neon would all have the same electron configuration. Therefore, we call them isoelectronic. So isoelectronic, they have the same number of electrons, therefore they have the same electron configuration. Now that's for your representative elements. It gets a little more complicated when we look at transition metals. So transition metals tend to lose the s orbital before the d orbital, because even though d has higher energy, it's more stable than having that extra s. So keep in mind that most transition metals actually form more than one cation, and so they're frequently not isoelectronic with noble gases. One example is manganese. Manganese's electron configuration would be argon 4s2 3d5. So manganese plus 2 is argon 3d5. Notice that we lose that s orbital because the d is more stable than that s. Now something else to keep in mind that they form more than one compound. Manganese will actually also form a plus 7. So when he does form his plus 7, he's going to lose the 2 from the s and the 5 from the d. So then he would be isoelectronic with argon. But the plus 2 ion is not isoelectronic with a noble gas. So it really depends on how many electrons they are losing as to whether or not they're isoelectronic with a noble gas.